New quantum paradox clarifies where our views of reality go wrong. A thought experiment has shaken up the world of quantum foundations, forcing physicists to clarify how various quantum interpretations, such as many worlds and the Copenhagen interpretation, abandon seemingly sensible assumptions about reality. That quantum mechanics is a successful theory is not in dispute. It makes astonishingly accurate predictions about the nature of the world at microscopic scales. What has been in dispute for nearly a century is just what it's telling us about what exists, what is real. There are myriad interpretations that offer their own take on the question, each requiring us to buy into certain as yet unverified claims, hence assumptions, about the nature of reality. Now, a new thought experiment is confronting these assumptions head-on and shaking the foundations of quantum physics. The experiment is decidedly strange. For example, it requires making measurements that can erase any memory of an event that was just observed. While this isn't possible with humans, quantum computers could be used to carry out this weird experiment and potentially discriminate between the different interpretations of quantum physics. Every now and then you get a paper which gets everybody thinking and discussing, and this is one of those cases, said Matthew Leifer, a quantum physicist at Chapman University in Orange, California. This is a thought experiment which is going to be added to the canon of weird things we think about in quantum foundations. The experiment, designed by Daniela Frochager and Renato Renner, of the Swiss Federal Institute of Technology Zurich, involves a set of assumptions that on the face of it seem entirely reasonable. But the experiment leads to contradictions, suggesting that at least one of the assumptions is wrong. The choice of which assumption to give up has implications for our understanding of the quantum world and points to the possibility that quantum mechanics is not a universal theory, and so cannot be applied to complex systems such as humans. Quantum physicists are notoriously divided when it comes to the correct interpretation of the equations that are used to describe quantum goings-on. But in the new thought experiment, no view of the quantum world comes through unscathed. Each one falls afoul of one or another assumption. Could something entirely new await us in our search for an uncontroversial description of reality? Art for New Quantum Paradox clarifies where reality goes wrong. Quantum theory works extremely well at the scale of photons, electrons, atoms, molecules, even micromolecules. But is it applicable to systems that are much, much larger than macromolecules? We have not experimentally established the fact that quantum mechanics applies on larger scales, and larger means even something the size of a virus or a little cell, Renner said. In particular, we don't know whether it extends to objects the size of humans and even lesser, whether it extends to objects the size of black holes. Despite this lack of empirical evidence, physicists think that quantum mechanics can be used to describe systems at all scales, meaning it's universal. To test this assertion, Frochager and Renner came up with their thought experiment, which is an extension of something the physicist Eugene Wigner first dreamed up in the 1960s. The new experiment shows that, in a quantum world, two people can end up disagreeing about a seemingly irrefutable result, such as the outcome of a coin toss, suggesting something is amiss with the assumptions we make about quantum reality. In standard quantum mechanics, a quantum system such as a subatomic particle is represented by a mathematical abstraction called the wave function. Physicists calculate how the particle's wave function evolves with time. But the wave function does not give us the exact value for any of the particle's properties, such as its position. If we want to know where the particle is, the wave function's value at any point in space and time only lets us calculate the probability of finding the particle at that point, should we choose to look. Before we look, the wave function is spread out, and it encodes different probabilities for the particle being in different places. The particle is said to be in a quantum superposition of being in many places at once. More generally, a quantum system can be in a superposition of states, where state can refer to other properties, such as the spin of a particle. Much of the Frochager-Renner thought experiment involves manipulating complex quantum objects, maybe even humans, that end up in superpositions of states. The experiment has 4 agents: Alice, Alice's friend, Bob, and Bob's friend. Alice's friend is inside a lab making measurements on a quantum system, and Alice is outside, monitoring both the lab and her friend. Bob's friend is similarly inside another lab, and Bob is observing his friend in the lab, treating them both as one system. Inside the first lab, Alice's friend makes a measurement on what is effectively a coin toss designed to come up heads 1/3 of the time and tails 2/3 of the time. If the toss comes up heads, Alice's friend prepares a particle with spin pointing down, but if the toss comes up tails, she prepares a particle in a superposition of equal parts spin up and spin down. Alice's friend sends a particle to Bob's friend, who measures the spin of the particle. Based on the result, Bob's friend can now make an assertion about what Alice's friend saw in her coin toss. If he finds a particle spin to be up, for example, he knows the coin came up tails. The experiment continues. Alice measures the state of her friend and her lab, treating all of it as one quantum system, and uses quantum theory to make predictions. Bob does the same with his friend and lab. Here comes the first assumption: an agent can analyze another system, even a complex one including other agents, using quantum mechanics. In other words, quantum theory is universal, and everything in the universe, including entire laboratories, and the scientists inside them, follows the rules of quantum mechanics. This assumption allows Alice to treat her friend in the lab as one system and make a special type of measurement, which puts the entire lab, including its contents, into a superposition of states. This is not a simple measurement, and herein lies the thought experiment's weirdness. Lucy reading a Candor Quantum magazine. The process is best understood by considering a single photon that's in a superposition of being polarized horizontally and vertically. Say you measure the polarization and find it to be vertically polarized. Now, if you keep checking to see if the photon is vertically polarized, you'll always find that it is. But if you measure the vertically polarized photon to see if it is polarized in a different direction, say at a 45-degree angle to the vertical, you'll find that there's a 50% chance that it is, and a 50% chance that it isn't. Now if you go back to measure what you thought was a vertically polarized photon, you'll find there's a chance that it's no longer vertically polarized at all, rather, it's become horizontally polarized. The 45-degree measurement has put the photon back into a superposition of being polarized horizontally and vertically. This is all very fine for a single particle, and such measurements have been amply verified in actual experiments. But in the thought experiment, Frochager and Renner want to do something similar with complex systems. At this stage in the experiment, Alice's friend has already seen the coin coming up either heads or tails. But Alice's complex measurement puts the lab, friend included, into a superposition of having seen heads and tails. Given this weird state, it's just as well that the experiment does not demand anything further of Alice's friend. Alice, however, is not done. Based on her complex measurement, which can come out as either yes or no, she can infer the result of the measurement made by Bob's friend. Say Alice got yes for an answer. She can deduce using quantum mechanics that Bob's friend must have found the particle's spin to be up, and therefore that Alice's friend got tails in her coin toss. This assertion by Alice necessitates another assumption about her use of quantum theory. Not only does she reason about what she knows, but she reasons about how Bob's friend used quantum theory to arrive at his conclusion about the result of the coin toss. Alice makes that conclusion her own. This assumption of consistency argues that the predictions made by different agents using quantum theory are not contradictory. Meanwhile, Bob can make a similarly complex measurement on his friend and his lab, placing them in a quantum superposition. The answer can again be yes or no. If Bob gets yes, the measurement is designed to let him conclude that Alice's friend must have seen heads in her coin toss. It's clear that Alice and Bob can make measurements and compare their assertions about the result of the coin toss. But this involves another assumption, If an agent's measurement says that the coin toss came up heads, then the opposite fact, that the coin toss came up tails, cannot be simultaneously true. The setup is now ripe for contradiction. When Alice gets a yes for her measurement, she infers that the coin toss came up tails, and when Bob gets a yes for his measurement, he infers the coin toss came up heads. Most of the time, Alice and Bob will get opposite answers. But Frochager and Renner show that in 1/12 of the cases both Alice and Bob will get a yes in the same run of the experiment, causing them to disagree about whether Alice's friends got a heads or a tails. So, both of them are talking about the past event, and they are both sure what it was, but the statements are exactly opposite, Renner said. And that's the contradiction. That shows something must be wrong. This led Frochager and Renner to claim that one of the three assumptions that underpin the thought experiment must be incorrect. Art for New Quantum Paradox clarifies where reality goes wrong. The science stops there. We just know one of the three is wrong, and we cannot really give a good argument as to which one is violated, Renner said. This is now a matter of interpretation and taste. Fortunately, there are a wealth of interpretations of quantum mechanics, and almost all of them have to do with what happens to the wave function upon measurement. Take a particle's position. Before measurement, we can only talk in terms of the probabilities of, say, finding the particle somewhere. Upon measurement, the particle assumes a definite location. In the Copenhagen interpretation, measurement causes the wave function to collapse, and we cannot talk of properties, such as a particle's position, before collapse. Some physicists view the Copenhagen interpretation as an argument that properties are not real until measured. This form of anti-realism was anathema to Einstein, as it is to some quantum physicists today. And so is the notion of a measurement causing the collapse of the wave function, particularly because the Copenhagen interpretation is unclear about exactly what constitutes a measurement. Alternative interpretations or theories mainly try to either advance a realist view, that quantum systems have properties independent of observers and measurements, or avoid a measurement-induced collapse, or both. For example, the many worlds interpretation takes the evolution of the wave function at face value and denies that it ever collapses. If a quantum coin toss can be either heads or tails, then in the many worlds scenario, both outcomes happen, each in a different world. Given this, the assumption that there is only one outcome from measurement, and that if the coin tosses heads, it cannot simultaneously be tails, becomes untenable. In many worlds, the result of the coin toss is both heads and tails, and thus the fact that Alice and Bob can sometimes get opposite answers is not a contradiction. Lucy reading a Candor Quantum magazine. I have to admit that if you had asked me 2 years ago, I'd have said, our experiment just shows that many worlds is actually a good interpretation and you should give up the requirement that measurements have only a single outcome, Renner said. This is also the view of the theoretical physicist David Deutsch of the University of Oxford, who became aware of the Frochager-Renner paper when it first appeared on arXiv.org. In that version of the paper, the authors favored the many worlds scenario. The latest version of the paper, which was peer-reviewed and published in Nature Communications in September, takes a more agnostic stance. Deutsch thinks the thought experiment will continue to support many worlds. My take is likely to be that it kills wave function collapse or single universe versions of quantum theory, but they were already stone dead, he said. I'm not sure what purpose it serves to attack them again with bigger weapons. Art for New Quantum Paradox clarifies where reality goes wrong. Renner, however, has changed his mind. He thinks the assumption most likely to be invalid is the idea that quantum mechanics is universally applicable. This assumption is violated, for example, by so-called spontaneous collapse theories that argue, as the name suggests, for a spontaneous and random collapse of the wave function, but one that is independent of measurement. These models ensure that small quantum systems, such as particles, can remain in a superposition of states almost forever, but as systems get more massive, it gets more and more likely that they will spontaneously collapse to a classical state. Measurements merely discover the state of the collapse system. In spontaneous collapse theories, quantum mechanics can no longer be applied to systems larger than some threshold mass. And while these models have yet to be empirically verified, they haven't been ruled out either. Nicholas Gizin of the University of Geneva favors spontaneous collapse theories as a way to resolve the contradiction in the Frochager-Renner experiment. My way out of the conundrum is clearly by saying, no, at some point the superposition principle no longer holds, he said. We have not experimentally established the fact that quantum mechanics applies on larger scales, and larger means even something the size of a virus or a little cell. Renato Renner, if you want to hold on to the assumption that quantum theory is universally applicable, and that measurements have only a single outcome, then you've got to let go of the remaining assumption, that of consistency. The predictions made by different agents using quantum theory will not be contradictory. Using a slightly altered version of the Frochager-Renner experiment, Leifer has shown that this final assumption, or a variant thereof, must go if Copenhagen-style theories hold true. In Leifer's analysis, these theories share certain attributes, in that they are universally applicable, anti-realistic, meaning that quantum systems don't have well-defined properties, such as position, before measurement, and complete, meaning that there is no hidden reality that the theory is failing to capture. Given these attributes, his work implies that there is no single outcome of a given measurement that's subjectively true for all observers. So if a detector clicked for Alice's friend inside the lab, then it's an objective fact for her, but not so for Alice, who is outside the lab modeling the entire lab using quantum theory. The results of measurements depend on the perspective of the observer. If you want to maintain the Copenhagen type of view, it seems the best move is towards this perspectival version, Leifer said. He points out that certain interpretations, such as quantum Bayesianism, or QBism, have already adopted the stance that measurement outcomes are subjective to an observer. Renner thinks that giving up this assumption entirely would destroy a theory's ability to be effective as a means for agents to know about each other's state of knowledge. Such a theory could be dismissed as solipsistic. So any theory that moves toward facts being subjective has to re-establish some means of communicating knowledge that satisfies two opposing constraints. First, it has to be weak enough that it doesn't provoke the paradox seen in the Frochager-Renner experiment. Yet it must also be strong enough to avoid charges of solipsism. No one has yet formulated such a theory to everyone's satisfaction. Art for New Quantum Paradox clarifies where reality goes wrong. The Frochager-Renner experiment generates contradictions among a set of three seemingly sensible assumptions. The effort to explicate how various interpretations of quantum theory violate the assumptions has been an extremely useful exercise, said Rob Speckens of the Perimeter Institute for Theoretical Physics in Waterloo, Canada. This thought experiment is a great lens through which to examine the differences of opinions between different camps on the interpretation of quantum theory, Speckens said. I don't think it's really eliminated options that people were endorsing prior to the work, but it has clarified precisely what the different interpretational camps need to believe to avoid this contradiction. It has served to clarify people's position on some of these issues. Given that theoreticians cannot tell the interpretations apart, experimentalists are thinking about how to implement the thought experiment, in the hope of further illuminating the problem. But it will be a formidable task, because the experiment makes some weird demands. For example, when Alice makes a special measurement on her friend and her lab, it puts everything, the friend's brain included, into a superposition of states. Mathematically, this complicated measurement is the same as first reversing the time evolution of the system, such that the memory of the agent is erased in the quantum system, such as the particle the agent has measured, is brought back to its original state, and then performing a simpler measurement on just the particle, said Howard Wiseman of Griffith University in Brisbane, Australia. The measurement may be simple, but as Gizin points out rather diplomatically, reversing an agent, including the brain and the memory of that agent, is the delicate part. Nonetheless, Jizin is not averse to thinking that maybe, one day, the experiment could be done using complex quantum computers as the agents inside the labs, acting as Alice's friend and Bob's friend. In principle, the time evolution of a quantum computer can be reversed. One possibility is that such an experiment will replicate the predictions of standard quantum mechanics even as quantum computers get more and more complex. But it may not. Another alternative is that at some point while we develop these quantum computers, we hit the boundary of the superposition principle and find that actually quantum mechanics is not universal, Jizin said. Leifer, for his part, is holding out for something new. I think the correct interpretation of quantum mechanics is none of the above, he said. A private view of quantum reality. He likens the current situation with quantum mechanics to the time before Einstein came up with his special theory of relativity. Experimentalists had found no sign of the luminiferous ether, the medium through which light waves were thought to propagate in a Newtonian universe. Einstein argued that there is no ether. Instead he showed that space and time are malleable. Pre-Einstein I couldn't have told you that it was the structure of space and time that was going to change, Leifer said. Quantum mechanics is in a similar situation. Now, he thinks, it's likely that we are making some implicit assumption about the way the world has to be that just isn't true, he said. Once we change that, once we modify that assumption, everything would suddenly fall into place. That's kind of the hope. Anybody who is skeptical of all interpretations of quantum mechanics must be thinking something like this. Can I tell you what's a plausible candidate for such an assumption? Well, if I could, I would just be working on that theory. Please save trees and nature. Please subscribe my channel. Thank you.